Greetings, everyone. We have had a postal service strike that lasted at least a month, and in the meantime, waiting for some other major components to build my 10 gigahertz tower mounted system, I decided that I would try to build a transmitter monitor. So basically a separate standalone 10 gigahertz receiver to check from distance, from the shack, that my transmitter that's located up on the tower is indeed transmitting with the right amount of power and on frequency. There's nothing new in using LNBs to detect 10 gigahertz signals, so I decided to take that avenue, experiment a little bit on a separate 10 gig receiver that I could receive with an SDR receiver, of course. So here's what I purchased, delivered by courier. It's a universal KU band. It's a twin output LNB FF4 feed horn. So it is a built-in satellite receiver for the KU band. It's a twin band unit. This thing costs $10 on AliExpress, delivery included, so it's very cheap. And with the slight modifications, you could use this to receive the Q100 amateur radio satellite if you wanted to, with slight modifications with the frequency reference that's built in. And we'll talk about this because I'm going to do that change also. Here are the specs. So yeah, it's universal KU band. It covers from 10.7 gigahertz to 12.75 gigahertz. So you can see that 10.7 gigahertz is not far from 10.368. So this issue with the waveguide and the minimum usable frequency due to cutoff of the waveguide, it shouldn't be a problem. I'm sure there's some margin in there. And it's a dual frequency LO. To be able to reach a 12.75 gigahertz frequency, you have to switch the LO frequency. And so this guy has two LO frequencies, 9.75 gigahertz, and this is the one we're interested in, and 10.6 gigahertz, which is the other frequency that's available for the LO. And if you do quick math, 10.368, our frequency, minus 9.75 gigahertz. So by receiving with an SDR receiver at 618 megahertz on either of the receive ports, we can pick up the 10.368 signal. So that should work. So with degraded performance, maybe, but this thing has a lot of gain. Clearly, they say gain 60 dB, and it's got a very low noise figure, 0.3 dB. Most people say that this is BS. It's probably closer to 1 dB. Regardless, it will be sensitive and low noise enough to pick up the 10.368 signal using this unit. So, here's what the plan is. I will feed 12 volts to this guy here, one of the ports, and 12 volts select the 9.75 gigahertz LO. If I put higher than, I think it's 16 volts DC here, it will automatically switch to the other frequency. So we could try both if we wanted to, but it's not required. Just 12 volts, 13, 14 volts is enough here. And we should see with a 10.368 source, we should be able to see something coming out of this port here. It will drift because this thing is free running. It's designed for satellite reception of a few megahertz wide signals. So listening to narrowband CW will move just due to temperature drift of the internal oscillator. But this unit has a 25 megahertz quartz crystal, and this is how we can modify it. Let's see later. Okay, let's quickly test this guy with an SDR receiver. Here's the setup I'm going to use. Looks complex, but it's not, okay? So I have my LNBF here. I feed this to a two-way splitter. It's good for up to 2400 megahertz, so that's not an issue. It passes DC. It's written on it, DC pass. So if I inject some DC here, it will go straight through the coax into the unit. As for the RF, since it's a splitter, I pick up the RF signal on the other port and I send this to the SDR receiver In this case, it's an RSP1A from SDR Play, but it could be RTL SDR. It would still work fine. And this is connected up to the computer. So DC sent to the unit, RF picked up and sent to the receiver. So I have a 10.368 single generator turned on. I will move this guy somewhat closer to the source, and let's see what we can pick up on the computer. So the SDR is powered up, and I'm using SDR++ software on Linux to pick up the signal. I'm tuned to around 618 megahertz, looking for the tone that comes from my signal generator, which has a short antenna just on the output, and the signal is being picked up by the LNBF. And as you can see, it's close, but it's not there. It's around 94 kilohertz, too low in frequency. Now this thing has had plenty of time to warm up. It's been like 30 minutes or something like that. You can hear the tone. I can move this thing around if you like. Okay, so clearly this is the tone. But look, there's some products here that are drifting slowly and surely. What they are, I have no clue. I don't think it's the SDR receiver. This thing is slowly but surely creeping into my passband. It's right here. So it's not surprising that the low-cost unit designed to pick up TV signals would also have some spurs show up. And now the spur is mixing up with the signal and it's giving us some weird pattern here. So anyway, it does work, no doubt. To show you how sensitive it is, because it's a free-running crystal, I'll disconnect it, the power, and reconnect and look at it drifting. And it will overshoot. And yeah, it will sort of come into, but drift again back, as you can see. This thing is all over the place, because of course you take the 25 megahertz signal and you multiply it by, so I did a cut in the video, look how much it shifted. So yeah, I was gonna say you take 25 megahertz and you multiply it by 390. So any drift on the crystal is multiplied by 390. So it doesn't take a lot to show up here as drift. The good thing about SDR++ is, of course, I can include an offset, and they have pre-defined offset for LNBs of 9.75 gigahertz right here. So once that offset is enabled, we can have a display showing 10.368, you know, which is pretty neat, and that's how I'm going to run it, of course. So can we stabilize that oscillator? And the answer is yes, for sure. And that's what I'm going to be working on next. So opening up that unit should be relatively easy. Yeah, relatively, because they don't use any glue. Clearly, it's just snapped in place. This thing can turn if I twist. So wish me good luck. I'm going to try to crack it open. Okay, first step was easy. With a opening tool, you know, and a screwdriver, I had no issue cracking open the case. We go slowly and no damage whatsoever. So I'm happy with that. I will be able to rebuild it. And they did go through the trouble of adding some sealant for the cap here, so that there's no water that goes inside the horn. And yes, by the way, the horn is the classic 2-probe with an added steel rod that goes across, with the objective, the steel rod, of course, of creating some sort of back wall for the front probe, and then there's a real back wall for the rear probe. Classic design. And now next step is to crack this thing open. I can see a screw here, a torque screw. There's another one here. There's another screw here. Is it an adjustment screw? I doubt, because it's supposed to be a crystal oscillator. And the reason why it's supposed to be a crystal oscillator is because it has 2 frequencies. So it takes some electronics to switch. It's not just a dielectric oscillator like the cheapest model single LO frequency. So this is kind of soft, so I can cut through, and I'll come back with the thing open. So next step, I managed to open it up. It was relatively easy, it just took time. I had to cut all the silicone all around, of course, and peel it off, try to remove as much as possible. But despite removing all the silicone, there was still some between the cover and the body, the housing. So it did take a bit of persuasion using a screwdriver inside the 3 holes to, you know, pull the thing away. And I managed to open it up without any damage or hurting myself with the X-Acto blade. Be careful, guys. When you cut anything, never ever have your finger, any of your hand, your fingers in the way, because if it slips, you're going to hurt yourself. Sounds obvious, eh? Believe me, when we work for a long period of time, all around, we tend to forget these things. And then, whoop, tool slips and you hurt yourself. Guys, believe me, I learned it 14 stitches later. I know what it means, okay? All right, back to what we were doing here. So I did expose the PCB, and no surprise, it's a 25 megahertz crystal. Let me zoom in. Yeah, so our 2 RF outputs are right here on the left. See, these rods here are the IF output going to the 2 connectors, which are outside of the frame. We have 2 voltage regulators, 1 for each of the 2 channels, and this chip does pretty much all the work. The conversion, so mixer is in there, the local oscillator is in there, and like I mentioned, no surprise, 25 megahertz crystal, and this is where we're going to bring in 25 megahertz. And if we look at the high speed, the 10 gig side, we have 2 probes. One is here going inside the waveguide, and the other one is right here. So it's 2 identical channels. They're not physically laid out the same, but it's identical, and the 2 channels go into that single chip. And so the first stage is a low noise amplifier, followed by the second stage here. And what you will notice is that this is a broadband receiver. There's no hairpin filter, bandpass filter of any kind. It's broadband, so no wonder we can pick up 10368 very easily with this design. So it's very simple, simplistic. Now, to inject the 25 megahertz, if we look at how it's built, there is symmetry on the crystal quartz. We have a pad with a capacitor to ground, probably around 10-15 picofarad. Same thing here, capacitor to ground, and then these 2 signals go in right under my red straw here. They go in a symmetry form, but it's not quite symmetric. One is actually an input, and the other one is an output that stimulates the quartz so that the whole thing oscillates at 25 megahertz. So we need to know which one is the input, which one is the output. And I did this. I probe with an oscilloscope right here, and then I probe here, and the amplitude at 25 megahertz was larger here than it was here. So what this tells me is that this is an output and this is the input. So X1 and then X2 if we want to identify these things. And there's a DC offset on both. No wonder. This thing has 3.3 volt guts inside. So we have to AC couple the 25 megahertz. Make sure we bring in through a capacitor, because this thing puts some DC on these 2 pads. Okay, so the plan is to remove the quartz and inject 25 megahertz and see if this thing works. All right, I'm done modifying the unit. I removed the crystal that was right here. I soldered it back to a piece of ground here, just so that I keep it with the unit in case I want to revert the modification. I'll still have the crystal right here. And notice I've also soldered the little capacitor right here. I kept it the 10-15 puff capacitor. The other one I left it on there because we don't need that pad at all. And I lifted up the center pin of this F connector. It's not soldered anymore. And I ran a piece of wire, 30 gauge, to a capacitor. What you see there is the vertical plane of a 1000 picofarad 1210 surface mounted capacitor. From a different angle you can see it's really a capacitor. And yeah, so I feed the 25 megahertz from the F connector through a coupling cap onto the input pad. And that's my mod. Yes, I could have purchased a better 25 megahertz crystal. That would be a possibility. of the same size, of course. That would probably work, and it would work much better, but it would still drift a little bit, whereas if I feed an external 25 megahertz GPS derived signal, it will always be on frequency regardless of the temperature. But yes, some people do this. They fit a 0.1 or 1 ppm crystal there, and that improves the stability and frequency accuracy of the whole unit. I prefer to use an external signal. Alright, I'll close the lid. Let's give it a try now. Let's go see if we can pick up a signal from the signal generator and see how accurate we are in frequency. So here's the result. I'm feeding 25 megahertz from a synthesized generator, and the amplitude I'm feeding is plus 3 dBm. There's a range between, I'd say, -2, -3 and plus 13 maybe. So I'm not feeding a very strong signal at 25 megahertz, and everything is working fine. I'm about 2 feet from the short piece of coax I use as an antenna for the 10368 generator. The generator is at -50 dBm, and like I said, I'm about 2 feet away and I can move. You'll see the peak will move, and I can rotate and get some more signal. There we go, because it's polarized dependent. And look at the frequency, 10368.000, right on. I did adjust a little bit the offset here by 450 hertz down, and that is really the RSP1A SDR receiver that has a little bit of an offset at 618 megahertz. It's enough to show. And if you want to see the resolution here, if I increase by 1 kilohertz, 2 kilohertz, 3 kilohertz, you see every vertical line is 1 kilohertz, so we're really in the right spot. So all in all, 25 meg is very stable. Now for generating 25 meg in a permanent fashion, here's my solution. To generate 25 megahertz with a 10 megahertz input, we have a few possibilities, but the one I've adopted a few years ago and I still use very often is an SI5351C. That's a synthesizer chip that can take an input reference. The A version of the chip doesn't have an input pin, but the C version does. So I feed a 10 megahertz signal into the SI5351C and program it using a PIC microcontroller that I soldered here. Program the chip, because it's power on programming, it doesn't have any flash or anything. Program it to produce 25 megahertz output with a 10 megahertz input. And the rest of the circuit was to use on an Ultimate 3S 2-meter beacon. It's a Whisper beacon, so Whisper Ultimate 3S Whisper box, and with this I stabilized the whole unit, and it's very effective on 2 meters even. But the second part of the circuit, which was an SI5351A and supporting circuit, plus how to connect it to the Ultimate 3S, that's not important anymore. We need the supply here, filtering, regulator, and the input, and the SI5351C, and the PIC microcontroller. LED is optional if we want to show that it's in lock. So that's what I will very likely use. Put that in a small box and feed 25 megahertz to the unit directly. That board and project for the Ultimate 3S Whisper Beacon is on my website, ve2zaz.net. So there you go. All we need is an external 25 megahertz signal here, which nowadays even using a signal generator can be done. And we have a unit that, with an SDR receiver, doesn't have to be on a ham band. In this case here, it's at 618 megahertz. That is fine, no problem. And of course, the unit is no longer water sealed, but we could do it with some silicone again, seal it up again, which I'm not going to do because I'm quite confident that from within inside, I'll be able to pick up my own signal when I transmit at around 10 watts. Should be strong enough to be picked up. If I pick up a weak signal in the -50, -60 dBm range, no issue whatsoever. With the gain brought down low on the SDR receiver, I shouldn't have any issue to pick up a high power signal from my shack, even if it transmits up on the tower. Now, I'll put it back together, easily done, and I'll work on a 25 meg, a permanent solution for that. In the meantime, well, thank you. See you soon. 7-3.